Hey guys, this is Mr. Lowry. This is a homework assignment that I handed out on day one. So for this week, day one for B day is actually on Tuesday, 2/16. If you're an A day, day one is going to come on a Wednesday. It's a weird week because we had President's Day on Monday. But this is going to build on an activity we did, a zombie activity, that was called Z+2. The fallout. This is the one with the radioactive material in the air that's decreasing. So just to kind of connect the two, at the very end of the last activity, we came up with an equation. And it was like the amount of zutonium after n years is equal to 60 times 1/2 to the n power. Something like that. Okay. We also, our graph looked something like this. We kind of started going down, it went down and it curved. Okay, so these are ideas about exponential decay that we're going to use. Now we don't want to forget what we talked about last week, because last week we talked about exponential growth. So we still have that. We're just going to add a little bit to that, and we're going to talk about exponential decay. So we talked about the form of writing exponential functions, and last week we wrote this little template out, a times b to the x power. And we talked about how a represents the initial amount. But last week we only knew about exponential growth, and so we called this number here, the b part, we called that the growth factor, because we were always growing. But in this case, we're getting less. We're halving every time, and so that one is going to be called exponential decay. So what we're going to put this here is we're going to put b represents the growth or decay factor. I'm making a video right now, so you're going to have to come back. Sorry about that. I just had a student walk in and I had to let her know that I was making a video. So anyway, this number here in this case is a decay factor. Okay, so a times b to the x is the form. A is the initial amount, b is the growth factor, but depending on whether this is bigger than 1 or less than 1 will depend on if it's a growth or a decay function. Okay, in this case we're halving, right? We multiply something by a half, it gets less, and so that makes it decay. So in an exponential growth function, b has to be greater than 1, right? So we were using an inequality symbol, that greater than. So, for example, with zombies, we had 1 times 2 to the n. We started with 1 zombie, and we were doubling n times. So when we multiply by 2, the amount of zombies gets bigger. But in the zutonium case, that we multiply by a half, and we get less zutonium. So for a decay function, b has to be less than 1, but we also want to say that it's got to be greater than 0 because we don't want it to be negative. Okay. So things that are, between 0 and 1 would be like a half, a fourth, a third, 2/3. You could even use decimals like 0.75 or something. Those would all be decay factors. Okay, so if you want to, you can just maybe list out some growth factors, anything bigger than 1, but some examples would be like 2 for doubling, 3 for tripling. But you could even have something like 1.1. If you multiply something by 1.1, it's going to get bigger. So that would be a growth factor as well. For here, b between 0 and 1, you could have, of course, a half if you're halving, or you could have a fourth or something like that. You could have 0.75. Anything between 0 and 1, if you multiply by that number, your amount is going to decrease. Okay, so there's just some examples here, but this is generally what needs to happen. Okay, one other thing to note is that in an exponential function, the variable is in the exponent. Okay, it doesn't mean that exponential doesn't mean that it has an exponent. It means that the variable is the exponent. Okay, so let me give you kind of an example. These two things look kind of similar, but they're not the same thing. This is not exponential. It does have an exponent. It's not an exponential function. Okay, this is an exponential function. Notice that the variable is in the power. Okay, this is called something else. It's actually called quadratic, but we'll talk about that probably a little bit more in 10th grade, maybe a little bit this year. Okay, so we're looking for a variable in the exponent. Okay, and it represents repeated multiplication by the growth or decay factor. Oops, I spelled decay wrong. D-E-C-A-Y. Okay, so let's take a look. Let's look at this Zetonium one for a second. Let's say that 7 years have gone by. Well, I'm going to do 60 times 1/2 to the 7th power, right? And 60 times a half 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 times a half, 7 times. That's what the exponent represents. So we usually have it as a variable in the function, but then if we have a specific amount of time, we plug that in and we figure out how much of our substance is left. We'll do an example of that down here. All right, so here we have a function, and it says find the initial amount and the decay factor. Okay, so the initial amount here is 200. We don't know what this is. It could be, radioactive material. It could be anything really, but the initial amount is 200. And since we're using a for initial amount, I'm going to write a equals 200. Okay, the decay factor is this part, the 1/4. So this function is fourthing every time, right? And we're going to get less and less. And then of course the variables in the exponent, and it represents how many times. Let me get a little closer. How many times we multiply by 1/4. So that's an x right there. Okay. All right. Now what we can do with an exponential function is we can evaluate it. We can take a number, we can plug it in, and we can see what that's going to come out to be. So this says use the function from problem 4, this function, to find f of 5. So f of 5 is equal to 200 times 1/4, but then we want to do to the 5th power, right? So this would be, if we're talking about radioactive decay, we could say something like, how much is left after 5 years or something like that. It's the amount of time that we've repeatedly multiplied by 1/4. So let me show you how to do that on the calculator. Let me grab one real quick. All right, so every calculator is going to be slightly different, but scientific calculators should have a power key, okay? And so we're just going to basically type this guy in. So we have 200. Now, if we want to do a 4th, there's a couple ways to do it. You could do parentheses 1 divided by 4, right? That's a 4th. And then you can use this button right here. So this has like X, and that has a little box over it. That means you can kind of pick what variable you want, and I'm going to pick 5. Other calculators, you might see something like this. It might be a button that looks like it has like A to the B on it, which means you can pick the power, or sometimes you might see like X to the Y or something like that. These are the buttons that allow you to choose what exponent you want. So obviously we have a squared button, but that only gives you a power of 2. We have an x to the 3rd button that only gives you a power of 3. This one will allow you to choose whatever exponent you want. Okay, so on this calculator, with the settings that it has, it's going to give you a decimal, and on ours we can change it to, it's going to give you a fraction. We can change it to a decimal by pressing this button right here. Okay, so this is going to come out to about 0.19, and so we can round it there. Okay, now you also have a fraction key on a lot of calculators, so another way you could have done this was 200 times, you could do 1/4. Now here's the tricky part. When you write a fraction like this with the fraction button, you have to come out of the denominator. See how my cursor is blinking in just the denominator? The next thing I want to write, I don't want to write it down there, I want to write it outside. Right? So there's my parentheses, and then again power button, 5th power, right, gives me my fraction, change it to a decimal. Okay, so that's kind of how most calculators will work. Now again, you may not have this exact calculator at home, but if that's the case, it'll be similar. Another thing you can do is you can go here, desmos.com, and then /scientific. That one has an exponent button that you can use. I think it looks like this, A to the B, or something like that. All right, let's go down and take a look at some of these functions, determine if they're exponential growth, decay, or neither. Okay, so what we're looking for is something that looks like this. F of x equals a times b to the x power. In other words, the variable x, or in this case, sometimes it's n or whatever, but the variable is in the exponent. Okay, so if we just look at all those really quick, okay, variable in the exponent, let me zoom in here. variables in the exponent, variables in the exponent, variables in the exponent. This one doesn't have a variable in the exponent. Neither does this one. It does have an exponent, but the variable is not the exponent. And this one does. So right off the bat, we can eliminate these. These are not exponential growth. So, or excuse me, it says, is it exponential growth, decay, or neither? It's not an exponential function at all. So it's not growth or decay. Now all the rest of them are exponential functions. The trick is to determine if it's growth or decay. And so what we want to look at is we want to look at the b part. Okay? We want to see, is that bigger than 1 or less than 1? Right? Remember up here we said it's growth if b is bigger than 1. It's decay if b is less than 1 but greater than 0. So let's find all the b's. So here's a growth factor. Okay, this one's kind of tricky. There's a fraction there, but that's the growth factor. It's 3, right? Okay, here, this would be a decay factor, because 1/2 is less than 1, right? And then here, this is also less than 1. So we got a growth, exponential growth, we got exponential growth, we got an exponential decay for number 9, and we got an exponential decay for number 11. Okay, and then of course neither and neither for 8 and 10. All right, 12 and 13 I want you to do on your own. You're going to make a table and make a graph. It's kind of like what we did in class here with Zetonium, but it's a much smaller table, much smaller graph. Okay, just keep in mind you're halving, so I'll help you get started. Okay, so we have 40 milligrams. Also, sorry, this should say 10 through 19, or excuse me, 12 through 19, because I added a couple problems and forgot to change that. But we have 40 milligrams of a radioactive substance with half-life of an hour. So here's time in hours. We want to go 0 hours, 1 hour, 2 hour, 3 hour, 4 hour. Okay, and if no time has passed, we still have our initial amount, right, which is 40 milligrams, because nothing's happened yet. But after 1 hour, we've halved, right? Half-life means we're halving. So after 1 hour has gone by, we have half of what we started with, okay? And you're going to continue that pattern. So you're going to have half of, 20 after another hour, and then after another hour, you're going to have half of what was left over there, and then half of that. And you're going to keep going, and then you're going to use those that table to plot some points and make an exponential decay. But remember what your exponential decay graph looked like with the zombie week activity we did. It's going to look really similar to that. Okay, you're going to continue answering some questions from that scenario. So what is the initial amount? Where do you see the initial amount on the graph? What is the decay factor? And just kind of answer some questions about that. And then you have another evaluate. So you're going to write a function and then use like your calculator to be able to find how much is left after a certain amount of time. Okay, so those work on your own. I think you can probably figure those out. Remember, the function is going to look like something like this. F of x equals a times b to the x. Here's your initial amount. Okay, you can look at a previous page and find out what that is. Here is your decay factor. It's the number you're multiplying by. Now, the kind of the trick here is that we're talking about half-life, right? So it doesn't specifically tell you what your decay factor is, but if you're halving something, you have to multiply by a half, right? So that's kind of a huge hint there. All right, let's talk about the graphing here, because last week when you guys did a similar assignment, I noticed a few people had some problems graphing. So let's take a look at that. When you look at a function, what you want to know, first of all, is is it growth or decay? So determine if the function shown is growth or decay. Then you want to find out the initial amount and then whatever that growth or decay factor is, right? So let's take a look at this guy. So we got initial amount, and then this is the growth or decay factor. In this case, it's decay because that's less than 1. And this is the initial amount. So I'm going to write decay factor for a fourth, and then this is the initial amount. Okay. So initial amount is like how much you have when like no time has passed, like 0 hours have gone by, or 0 days, or whatever happens to be. So if my initial amount is 16, I start with 16 whatever, grams, zombies, whatever you want to talk about. Okay, so this initial amount is your y-intercept. That'll actually help you with one of these questions up here as well. Okay, your initial amount is your y-intercept. Okay, so if this is my initial amount, 16, my y-intercept then will be 0, 16. All right, now the next piece is how do you find the next number? So we're going to go to the right one, and every time we go to the right one, we're going to multiply the previous amount by 1/4. Okay, so this guy tells me what to do. I start with 16, okay, and then for the next one, I'm going to have 16 times 1/4. Now you could use a calculator for that, or you could, you should be able to do this, by hand. 16 times 1/4 is 16 over 4, or 4. Okay, and so my next number, when I move over to the right one, I go up to 4. So I am at 1/4 of what I previously was. Okay, and then we move over to one to the right and we do it again. So the next one, I'm going to have 4, the previous amount, times 1/4. Right? Again, you can probably do this by hand, but this is going to give us 4 times 1 over 1 times 4, 4 over 4, which is equal to 1. Okay, so when I go over here, when I move 1 over, I'm now at 1. So notice I go from 16 to 4 to 1, right? Keep on going. So if I wanted to, the next one I would take 1, and I would multiply that by 1/4. Every time we move over, or like, this is kind of like going down in the table, I multiply the previous amount by 1 over 4. Okay? 1 times 1/4 is 1/4. So my next value would be at 1/4. Now if this is 1 and this is 2, then 1/2 would be about here, and so 1/4 is going to be way down. And notice it looks a lot like my Ztonium graph, right? This is what an exponential decay curve looks like. Starts out kind of steep, goes down, levels out towards the bottom. Okay, so that is how you do an exponential decay. You got to find out, first of all, where do you start, where's your initial amount, and then you use the growth or decay factor to figure out your next values. Okay, let's do another one. Okay, let's take a look at number 23. Okay, so again, initial amount, 4. Decay factor, this time 1/2. So this is initial amount. And remember, initial amount's my y-intercept. So 0, 4. This is where I'm going to start. And I'm halving every time, right? So when I move over 1, I'm going to be half of what I was before. I was at 4, now I'm at 2. So I start with 4, and then I have 4 times 1/2, which is 4 over 2, or 2. Okay. And then I do 2 times 1/2. Right? 2 times 1/2 will be 2 over 2, or 1. So when I move over this one, I got to go up to 1. All right, and then I got another one. So 1 times 1/2 is 1/2. So I go from 4 to 2 to 1 to 1/2, right? 4, 2, 1. 1/2 would be like halfway between 0 and 1, or 0 and 1, so something like that. All right, now the thing that's different a little bit about this graph than the one in your zombie week activity is that we actually can have negatives over here. So if I'm going this way and I'm multiplying by 1/2, if I go backwards, I'm just going to kind of undo that. So multiply by 1/2, multiply by 2. If I want to go in reverse, I just need to do the opposite of multiplying by 1/2, which would be doubling. So if you think about it, before it was at 4, it had to be twice as big. So if I go back to the left, it should be up here at 8, right? Because that's twice as big as 4. And one more time, if I go back 1, I need to be twice as big as 8, which would put me up here at 16. So we do have numbers on both sides of the graph, that's fine, but check it out. If I go from 16, and then I half it and I get 8, and then I half it and I get 4, and then I half it and I get 2, that follows the pattern, right? So my curve is going to look something like this. Right? Now, again, I have stuff on the left-hand side, and that's okay. We don't know specifically this is talking about time or zombies or Ztonium or whatever, so that's just fine. But this is the key. This tells you, what to do as you move to the right. Okay? If you want to go backwards, it'll tell you what to do. You got to do the opposite, basically. All right, now some in here, some of these are exponential growth, so you kind of have to do both, right? So in this one, notice initial amount, right? And this is a growth factor because it's bigger than 1. So I'm not getting smaller here, I'm growing. I'm multiplying by 3, I'm tripling every time. Okay, so let's start with our initial amount, right? 2 initial amount, that's our y-intercept. Okay, so there we go. And then every time I move 1 unit to the right, I have to triple the number I had before. So I started out with 2, okay, then I have 2 times 3, which will be 6. So if I move over 1, I should be up at 6. Okay, don't go up like by 6, like don't count 1, 2, 3, 4, 5, 6 from here. Just go up to the number 6. Okay, and then I got to triple again. So now I take 6, the previous amount, and I multiply that guy by 3, and that gives me 18. Right, so if I go up over another one, I got to go all the way up to 18. Okay, and then we can triple again, 18 times 3. The problem is 18 times 3 is going to be off the graph. It's not going to fit anymore because these things go pretty fast. So that's going to be, that's 54, and that, we couldn't graph. But if we had enough room, we would go over 1 more, and then we go up to 54. All right, so that's what's going on here. Now notice that I'm doubling, right? So if I want to continue that pattern, I just need to go backwards. Sorry, I'm tripling here. Yeah, tripling, which is fine. That's what we did. If I want to know, what we have before that, we can go backwards here. So let's take a look. This way, I'm multiplying times 3. If I want to go the other way, left, that's like kind of going back in time almost. I need to do the opposite. So that's either multiply by 3 or like divide by 3 or, multiply by 1/3 or divide by 3. So here, if I do 2 and divide it by 3, I get 2/3, right? So that's kind of weird. But basically the graph is going to continue on this side as well. It's going to get into fraction land, but we're going to have values on both sides. So if I take 2/3 and I triple it, I get 3. And then I triple it and I get 6, and I triple it and I get 18, and I get 54, and so on. Okay, so that's how you do an exponential growth and decay. You got to start with your initial amount, which is that first number. The next number will tell you how to get to the next value, right? It's either bigger than 1, which means it's a growth factor, or it's less than 1, bigger than 0, which means it's a decay factor. And you just repeatedly multiply by that number to get the next y values. Okay. All right. Hope that helps. So this will be due on Wednesday if you're a B day. This will be due on Thursday if you are an A cohort. So we got a lot on it there. You got to do a couple more graphs and then answer some of these questions about this specific scenario. All right. I'll see you guys back in class for another Zombie Week activity later this week.